This is 3.2, Day 4, Computer Output and Regression to the Mean. There's an SEC football example on the page before this one, but I'm going to leave that example to you, since you should have all the tools you need to solve it on your own. So we're going to start on this page with interpreting computer regression output. It says a number of statistical software packages produce similar regression output. Be sure you can locate a few specific things, starting with the slope, the y-intercept, the value of S, remember that's the standard deviation of the residuals, and the value of R squared, our coefficient of determination as it's called. And then once you understand the statistical concepts, you can read and work with almost any software output. So that's encouraging. Okay, so here's some software output for the SEC example from the previous page. It says identify the values for slope, y-intercept, S, and R squared. So in the SEC example, points per game was on the x-axis. So if we align the points per game row here with its coefficient, the coefficient on the x value is always the slope. So our slope would be 0.43721, this value. And then the constant term is always the y-intercept, so our y-intercept then would be negative 3.751. And then S, although it's not lowercase, would be this value right here. So that's our standard deviation of the residuals. Last but not least, hopefully it's kind of obvious to you again, and I know it's not in lowercase here, but this would be our R squared value, which is our coefficient of determination. We don't need this R squared adjusted thing. You can pretty much throw that out for this class. In fact, at this point, we can pretty much ignore all this other stuff. We found the slope, the y-intercept, S, and R squared. So it outputs a lot more things that at this point in time we don't need. Okay, and if we look down here at example 3, it still uses the same SEC football data, but this is a different stat software or different output from a different stat software. It's called JMP. So let's point out those key values again. For starters, R squared is the very first thing. And that's the same value for R squared that we saw above. R squared adjusted we don't need. But then if we look at the next item here, it says root mean square error. So if we think about that, root is referring to square root, mean is the average, and then square error is talking about the residual squared. Remember, the residual is sort of like our error when we make predictions. So this is actually referring to the value for S, the standard deviation of the residuals. N would be the sample size here, right? Observations. So that'd be 12 observations for the 12 teams in the SEC. Our y-intercept, right? It says intercept, and then there's the estimate, and then estimate that goes with points per game. That would be our slope. Okay, so the next page has an example about Mentos and Diet Coke. Maybe you have or haven't done this experiment or you're familiar with it. It says when Mentos are dropped into a newly opened bottle of Diet Coke, carbon dioxide is released from the Diet Coke very rapidly, causing the Diet Coke to be expelled from the bottle. Will more Diet Coke be expelled when there's a large number of Mentos dropped in the bottle? Two statistics students, David and Rachel, decided to find out. Using 16-ounce or 2-cup bottles of Diet Coke, they dropped either 2, 3, 4, or 5 Mentos into a randomly selected bottle, waited for the fizzing to die down, and measured the number of cups remaining in the bottle. Then they subtracted this measurement from the original amount in the bottle to calculate the amount of Diet Coke expelled in cups Output from a regression analysis is shown below. So plot here, see the results from when they put 2 Mentos in, or 3 Mentos, or 4 Mentos, or 5 Mentos. So there's a positive association. Basically, the more Mentos they put in, the more Diet Coke was expelled. And there's the residual plot for the same data. So part A says, what is the equation of the least squares regression line? Define any variables you use. And here's the computer output that goes with it. So we can start with Mentos was the x value, so the coefficient on the x value would be our slope, and then the constant term would be our y-intercept. So we could say y hat equals, and our y-intercept is 1.00208 plus our slope times x. And if you want to put that in front of the y-intercept, that's totally fine also. If you're more comfortable writing y equals mx plus b, the order won't matter. We do have to define any variables we use. So in this case, we have to say, or y hat represents the predicted, that's the key word there, y hat represents the predicted amount of Diet Coke, and x is the number of Mentos that were dropped in. Part B, what's the correlation? So that's R. We're not given R here. We are given R squared though. So to get R, we would just have to take the square root of that value and make sure we get the correct sign, whether it's positive or negative. So if R squared is 0.602 as a decimal, the square root of that would be about 0.78 for our R value. And just to be clear, this is positive because the scatter plot showed a positive association. So part C asks, is a linear model actually appropriate for this data? Explain. Well, if we look back at the residual plot, that's exactly what this question refers to. Is the residual plot okay? Does it show a random scatter of points, or does it seem to show like some curved or some weird pattern? And I know these points are kind of stacked up here, but you should expect that because there were only a few options for Mentos, 2, 3, 4, or 5. So the fact that they're stacked up, that doesn't imply that there's a pattern, right? There's still a random scatter around that residual equals 0 line. So when you see a question like this, is a linear model actually appropriate? That is really asking you to refer to the residual plot. In this case, yes, a linear model is appropriate because the residual plot shows a random scatter about the horizontal or the residual equals 0 line. Okay, so what about part D here? It says, what percentage of variation and the amount of Diet Coke lost can be accounted for by the least squares regression line relating the amount of Diet Coke lost to the number of Mentos dropped into a bottle of Diet Coke? So that's a really long question just to ask you about what R squared is. Right? The coefficient of determination. What's R squared? So when you see a question that says, what percentage of variation, and then it gives you the context, that's referring to R squared. So as a percentage, we can say R squared is 60.2%. All right, and then the last item on this page, part E says if the amount expelled was measured in ounces instead of cups, how would the values of R squared and S be affected? So if we change the unit of measurement, if we measured it in ounces instead of cups, how would R squared and S be affected? Well, we know R squared would stay the same because it doesn't have any units. So if you change the units of measurement, it won't matter. R squared doesn't have any units. Similarly, the R value, the correlation coefficient, wouldn't be affected either. So R and R squared would stay the same. So no change for R squared. But S would actually be changed, right? The standard deviation of the residuals would actually be changed because it carries units. So S would be changed because it carries the same units as the Y variable. So if we think about the standard deviation of the residuals, when we say on average how far off we are in our predictions, we predict, so 1 cup is actually equal to 8 ounces. So we could just multiply the standard deviation by the absolute value of 8, which is just 8, right? So a fancy way to say, if you change the units, multiply it by the absolute value of whatever the unit change is. So our S value was 0.0672442. Just take that and multiply it by 8. So the new standard deviation, if we convert this to ounces, would be 0.5379536 ounces. Moral of the story, if you change the units of measurement from cups to ounces, R squared and even R would not be affected, but S, the standard deviation, would be affected.